Okay. So just before I start, I wanted to address your question. Yeah. So, I mean, this psi, deep psi you mentioned is actually BRST exact. Yeah. For example, I remember our BRST was psi, I mean, the twisted theory. It was psi dx bar, right? So now if I take psi dx, okay, and take the OPE of this, okay, so I have to integrate, right, contour integral around that. So I'm going to get, so let's say this is z, w, so 1 over z minus w square. Right. So you'll get here psi z and psi w. Do the contour integral, you'll get deep psi at w. Yeah, so that's actually in general one can prove the following thing, that if I have a, so this let me just call it, okay, I was calling q hat, let's say. So suppose I have a q hat acting on some v which is equal to 0. And suppose further that L naught hat, I mean again this is a twisted v is not equal to 0. It's some delta, let's say delta hat times v, where delta hat is not 0. Okay, then you can write this v as 1 over delta hat with, I think, so let's say this is w, this is z minus w, g plus, acting on v. Contour integral. So then, sorry, this is, let's call this as v hat or something, huh? Okay? Then you can show that v is equal to q v hat.
So it is essentially like the Witten index, which is concentrated at the energy.
Zero, yeah, correct. Of course, this is, when I say energy zero, I mean the operator psi. Psi is surely in the kernel of Q, right? And it's dimension 0. It has dimension 0. So it's not, you cannot write it as. But this is a dimension 0 version. So just like in usual string theory, we have for every vertex operator, we have the dimension 0 picture. I mean dimension 0 form of that, right? Which you multiply by C. I'm just looking at the left moving sector. There will be similarly right moving sector. So this will have dimension 0, because this is dimension 1, so this combination has dimension 0. And so this operator will be inserted at a point. You don't integrate that operator, right? But the version where you integrate it, that you get by applying b minus 1 on this guy, right? So this will have dimension 1, and that you integrate, right? But then if you look at the BRST acting on this object, it is not 0. It's a total derivative, right? That's exactly what happens here. I mean, you have this operator, which is, you have to put it at a point. You're not integrating over. But then there is another operator, which is dimension 1, which is to be integrated over. And that operator is simply dx, right? Because let me see, side bar x. Yeah. This operator, if I apply now q BRST, q hat, it will be psi dx bar, so it will have a double pole, right? So when I do the contour integral, this is just going to give me deep psi. So it's a total derivative, right? So that is the dimension 1 version. And that is a modulus, right? Dx, yeah, I mean, so exactly. I mean, no, sorry, maybe I didn't understand the question. But, G minus. Exactly, precisely. That's exactly the analog of this, because G minus is playing the role of B. That's the analogous of that statement. Yeah, exactly. So it's a dimension 1 version of this, right? So dx. Okay, so in fact, I mean, you can see that from the NSR formulation, the operators that you write which are in the -1 picture. This will be the operator for the -1 picture, right? And those will be those with a charge +1. Because -1 picture, this will have dimension half, which is what we have here. And then there's a -1 picture. So that makes it, the whole thing together makes it dimension 1, right? So just take not the ghost part, but just the matter part of it. And that would be dimension 0 in the L hat, from the L hat point of view, right? And that you insert at a point. Yeah. Okay. So now, what I will, so we, as we said, so we'll need, so the strategy is that, so we have a physical string, and we had a guess that we are computing term, what we should be doing is computing a term which has 2 Riemann tensor square. These are all, there's a particular self-duality property. Huh? So either they are all self-dual or all anti-self-dual. Huh? So you take that, and then you have the graviphoton field strength, which is again the same self-duality property, square to the power of g minus 1. So this is what we should compute, and hopefully this will be related to the topological partition function. So this, when I compute this amplitude, this should give me something like fg. Okay, so that's the question mark here. So this is what we are aiming to do. Now, on the other hand, you see this identification on this side, this is the topological side, all the dimensions are integers. There is no half integer dimension, right? Because as we saw, psi has become dimension 0, psi bar had dimension 1, right? Whereas in the untwisted theory, here, psi and psi bar both had dimension half, right? And when you have dimension half, you have this notion of spin structures, okay? So you have this even and odd spin structures, and you have to sum over all spin structures, right? So on this side, I have the sum over all spin structures. On this side, there is no notion of spin structure, because they're all integer dimensions, okay? So if at all we are able to show this equivalence, that will be only after doing the spin structure sum, okay? So we need to do the spin structure sum. Then hopefully we'll be able, so the strategy would be that you write down the expressions for the amplitude here, okay, after extracting the right powers of momentum. So you take the right powers of momentum out, then set all the momenta to 0, okay? And then you do the spin structure sum. You'll get some expression here. Then you compare that expression with what you would compute here, right? And hopefully show that the two things are the same. So that's the strategy. Now, in order to do all this, we'll be using, as I said, Berlinde squares, the chiral bosonization results. Okay. Now, in this chiral bosonization results, there will be, I'm not going to go through the proof of that. I will just state the things. But even to state the results of this chiral bosonization, I will need to introduce some symbols. Some mathematical quantities. Okay. So today I'll be just introducing those quantities. Then tomorrow I will describe the results of this and motivate why that result is correct. Okay. And then go on with this calculation. Okay. Sorry, where is the here?
Spin structures appear in NSR formalism.
Yeah.
If you could do, in principle,
correct.
computation
Sure.
in the Greens Theorem.
Yeah. That would be probably more direct. Yeah. If one could do that, yeah, correct. Okay, so some basic introduction to the higher genus surfaces, G greater than 1 surfaces. So let me just call it sigma G. Okay. Sigma G, so I just draw this picture here. I'm just going to draw genus 2, because otherwise, okay, you can keep adding handles. Now, you can see here that I suppose everyone is familiar with the genus 1, right? G equal to 1, where you have the theta functions and all these things, right? So our aim now is to introduce all of these things that we knew in genus 1 and generalize it to higher genus. Okay? This is the first aim here. So first of all, you see that there are several cycles which you cannot shrink. There is this cycle, there is this cycle, there is this cycle here, and there is this cycle here. You cannot shrink these cycles, right? So let me just call this, choose a basis. I will call this A1, B1, this one. And this is A2, and this is B2. In general, if I have genus G, there will be GAAs and GBs. So I will denote the cycles by AI and BI, I going from 1 up to G. Yeah, but that you can, I mean, this is the basis. This is the basis. That you can, so you're talking about this cycle here, right? This cycle, you can write it as combinations of the other cycles. So this provides a basis. Yeah, H1 is dimension of H1 is 2G. Then, of course, there will be on the, so this would mean, of course, there exists one forms, alpha I and beta j, beta I, let's say, such that integral of alpha j is delta ij. You can choose some basis here. This is the basis for the cohomology. And similarly, beta j bi equal to delta ij. And beta integrated over a is 0 and alpha integrated over b is 0. So it's just a basis, dual basis. There's a dual relation between homology and cohomology. Okay, you can choose that. Then the other important thing is that these are complex manifolds, right? Just like in the torus, we could introduce z and z bar coordinates, right? It's a complex structure. Okay, so oh no, at the moment I'm just talking about the real. These are real. I mean, so far I have not introduced a complex structure, right? Yeah, so that's what my next point was. That so now you can, these manifolds are complex manifolds. What it means is that if I write down some patches, if I cover this, make an atlas, draw an atlas, make some cover, then if you look at the overlap, so on each cover you can introduce some z coordinates, right? The overlaps are such that the coordinate here is a holomorphic function of the coordinate there. Okay? So the transition functions are holomorphic. Okay? So and that you can put complex structure here. Okay? So this is a complex manifold. So choose some complex structure. It's not unique. In fact, that is what gives the moduli of the Riemann surface. It turns out there are 3G minus 3 complex moduli space is 3G minus 3 complex dimensional space. So 6G minus 6 real. I mean, one can get an intuition for this moduli by representing this as, take a genus G surface you can think of as a sphere. You cut out 2G disks and connect pairwise by tubes, right? And in that case, you can just check how many moduli are there. So you have 2G points on a sphere. So first of all, you have 2G complex variables to describe the center of the disks, right? But on the sphere there is an SL2C symmetry, so you can fix 3 of them. So it's actually 2G minus 3. But then the tube will have the length of the tube and the twist, relative twist. Okay, so that will be one complex again. Okay. So that way you get 2G minus 3 plus G complex. So that's a 3G minus 3 complex moduli. Now, with respect to this complex structure, whatever complex structure you have chosen, you can find holomorphic. You can take combinations of these guys such that you find a holomorphic differentials, one differentials. So so what you'll have is G holomorphic one forms or one differentials one differentials I call it. So I call omega z. And then, of course, there will be complex conjugate, omega z bar, omega I. Now, these omegas, they transform as a one differential. What it means is that what is invariant is omega z dz. So if I look at these two different patches, in one patch I have a coordinate z, another patch I have a coordinate z prime. And if I look at the overlap here, then omega z dz will be the same as omega z prime dz prime. Okay. So this omega z is defined on this patch, first patch, and the second patch is here. So I don't know, let me call it first patch and second patch. And the relation between these will be given by that. So that is what we mean by, okay. So we know there are G holomorphic differentials here. Okay. So that's the one differentials. What about the functions? These are the easiest ones, right? So the functions means f of z is equal to f2 z prime. Okay. So by this, of course, I mean a point here whose coordinate with respect to the first torus is z, and the same point with respect to the second coordinate patch is z prime. And the functions are the same. That's what we mean by function. So now you can ask the following question. What are the holomorphic functions? Do they exist? Any holomorphic function? And of course, we know the only holomorphic function on a compact space is a constant. Right? So the only holomorphic function, holomorphic means a d bar acting on that function is 0. Right? So holomorphic function on sigma g is constant. So it's one-dimensional. I mean, the space of holomorphic objects is simply one-dimensional. One-dimensional because constant can be anything, right? So it is one-dimensional. The only holomorphic. Okay. Now, yeah. But this is not the whole story. In string theory, we know we have many different types of objects. For example, BC system. B has a dimension 2, so it's a quadratic differential, right? So that is there. And similarly, fermions, psi's are half differentials. Psi basically transforms like dz to the half, right? So psi z at dz to the half will be equal to psi z prime dz prime to the half. That will be the relation. So we have to deal with the more general objects. So those will be basically, I mean, this is what in mathematics they would call line bundles. So these will be some sections of different line bundles. Okay. So in particular, first let's see. So there will be different line bundles. Okay. Some line bundle, let's call it L. Okay. It will have some. If you look at some section of the line bundle L, let's call it S. Then again, the important property is that S evaluated at S in the overlap region. So if I look at S as a function of Z, then in the overlap region, S of Z and S of Z prime will be related by a transition functions which are holomorphic. Okay, that is the important point. So the transition functions will be holomorphic. In the overlap region. Okay. Now, one question one can ask is, can we classify all these different line bundles? And it turns out on genus, on the Riemann surface, it's pretty, I mean, one can do it pretty easily. So to do that, let's first, so the way one can do is the following. Take any section, any meromorphic section, Okay. But before I discuss that, let me first discuss the meromorphic functions, because that will be easier to understand. So let's take a function. So function is a particular case where the transition function is simply identity, right? These transition functions. So function, of course, we said holomorphic function, there is only one-dimensional. But you can now talk about meromorphic functions. Okay, let's say meromorphic function f. Now this f will have some poles, right? And possibly some zeros. Okay. So let's call the positions of the zeros. So these are the zeros at this, and poles at qi, let's say qj or something. These are points. Now, what I will do is, some of these poles may be of higher order, right? So what I will mean by that is, if suppose it is nth order pole, that means near the point qj, function go like z minus qj to the power of, say, n. Okay, this will be nth order pole, right? What I will do is I will call this as simply n times qj. So in other words, I put qj several times. Same qj, n times. So I'm going to count this with the multiplicities. Okay. So or if you don't want, you can just put n here, n qj. Okay. To remember that it is an nth order pole. Okay. Or you just repeat qj n times, is the same thing. So in order not to write this n, I will just repeat this qj n times. And same thing with the pi. If there is a mth order 0, it will be z minus pi to the power of m. Then I will put here either m, or I repeat pi m times. Okay? These are called the divisors. So divisors, the notation here is, you write divisors as sum over pi minus sum over qj. So for the zeros, you put a plus sign, and for the poles, you put a minus sign. So by looking at this expression, you immediately see these are the singularities, and these are the zeros. So that's what's called the divisor. Okay, and this sum is going over all the range of I and the range of j, whatever the number of poles and things are. Eh? Yeah, let's take sections which have only finite number of poles to begin with.
You have a function with a second singularity.
Yeah. So take finite number of things, right? So now, question is, can we say something about it? Can we, for a meromorphic function, can we say some relation between the number of poles and number of zeros and number of poles? Answer is yes. You can prove that the number of zeros will be equal to the number of poles. Okay, and that's very easy to do. Let's see. Let's just do here. You can just take this f, the section f, and take the df over f and integrate over the whole. So I have to draw the picture here a bit. So one convenient way of thinking about this is to, maybe I erase this so that one can see better. So the one way to think about this is, and this is very useful in proving various theorems, is choose some base point. I call it P naught, not to confuse with that P. Oh, sorry. I don't know. This has nothing to do with the zeros of the, okay? Okay. P hat, yeah. P hat naught. And then draw A cycles, everything starting from, so this is A1. The B1 would be, let's say, this something like that, B1. And same thing, A2 and B2. B2. Okay. And then cut this Riemann surface, cut open along these curves. And then open it up. What you will get a polygon. And that polygon will have a shape like this. So it will be, it's a genus 2 case. It will be 1, 2, 3, 4, 5, 6, 7, 8. So the way to understand this, these are all points P naught, P hat naught. These are all P hat naught, all these vertices. Okay. Now, so take this, for example, let's call this A1 cycle. So you cut it open, but then it splits into two parts. Okay, so this is coming from, say, the left part. Okay, then you go around the B1 cycle. Okay, again on one side, left or right. Then go backwards along the A1 cycle. So this is B1, then A1 inverse. Okay, and then again go back B1 inverse, and then repeat the same thing over on the second handle. So you'll have A2, B2, A2 inverse, B2 inverse. This is a very convenient picture, very useful picture, and many proofs, although, I mean, I will not be proving most of the statements. I will just state. But, okay. So now what we want to do is we want to integrate df over f around this boundary or this polygon. Okay. Now, you see the orientation is changing here. When I say A1 and A1 inverse, so on one side, let's call this as the A1, this A1. But then when I come back after the B1, then I go in the opposite direction. That's why I'm putting here A1 inverse. Okay. So this integral and that integral should cancel. Why? Because this is a function. Function is the same value on both sides, right? So, and since the orientation is opposite, they will cancel. So the result of this integral is actually equal to 0. Okay. On the other hand, what is this computing? This is nothing else but d log f, right? D log f. And it will, now look at the interior. Interior, there can be various poles, I mean, zeros and poles of this function, right? But when you take the d log f, every zero will come with a plus sign, and I do the residue, I mean, so you'll just get the residues, right? So this will be the sum over pi and qi, the various poles and the zeros, and you'll just get the residues. And so from this, you see each I mean, it will, yeah. So let's take for the first of all simple poles. So either first order zero or first order pole. Then you will get, for each p, you will get a +1, and for each q, you will get a -1 for each p. Okay. If it is, say, some mth order 0, I will get m. But that I already mentioned that I will put that m here, or repeat pi m times. Okay. That's what I'm saying. So, okay, I will just keep it like that. Then, so what it is counting is the sum of all the zeros minus the sum of all the poles. And that should be equal to 0. Okay. So this will be equal to the number of zeros minus the number of poles. Okay. So that's the... Okay. So we conclude that for the device, any meromorphic section of a function will have this property that the corresponding divisor has a degree 0. Degree is the sum. Okay, I mean the number of zeros minus number of poles. Okay, so that degree is always 0. So degree of the divisor for any meromorphic section function will be equal to 0. Okay. Yeah. Sorry. So let's look at this function, behavior of this function near one of the p's. P's are the zeros, positions of zeros, right? So function f will look like z minus pi to the power of 1. Huh? Or in general, if I have a mth order 0, it will be m. Okay. Now, if I take the log, this is a log of that, no? Log of f, take the derivative, I'm going to get, so d log f will be m over z minus pi. Right? And then there is always 1 over 2 pi I. 1 over 2 pi I will set to 1. So really, I should do 1 over 2 pi I. So it counts. So it counts this number of zeros, this one. And when I have a pole, it will be 1 over z minus qi to the power of. Huh?
You can say simply that
M is negative. Correct. Yeah, yeah. Correct. Okay, so that's why there's an opposite negative sign for that. So that's what's called the degree of the divisor. And what we are saying is that for the function, the degree will always be 0. Okay, now let's take some line bundle L, and it will have some sections. So take some line bundle L and take again some section of the line bundle L. It'll have some poles and some zeros, right? So the corresponding divisor D corresponding to this L, because this is related to, different line bundles will admit different types of sections, right? So this will be the number of, say, let's again Pi minus Qj. So these are the zeros of S, and these are the poles of S. Okay. Now, if I have a section like this, now, of course, the question is now, can I label, given a section L, given a line bundle L, is it unique? Is this divisor unique? Or, of course, you don't expect that, right? Because there must be lots of sections, right? And so what is the relation between them, right? Now, let's suppose I have two sections, S1 and S2, of the same line bundle, okay? Now, if I take so S1 will have some divisor, say D1, and again, D1 of L, and this will have some D2 L, right? Can we say something about some relation between these two? Well, that is easy to see, because if I divide S1 by S2, that's going to be a function, right? Because whatever transition functions are appearing here, they will cancel with the transition functions appearing here, right? When I go from one chart to another chart, one neighborhood to another neighborhood, there will be transition functions associated with that, but that will cancel with the transition functions here. So this will be an ordinary function. Okay? That means, let's call this now f. So, on the other hand, divisor of f, we know has degree 0. Okay? It will be, something. Okay, so, it will have degree 0. So one thing we immediately see, on the other hand, look at this S1 over S2. Where are the poles and the zeros? It will be simply and look at the divisor of this, it will be the sum of these two divisors. Difference of these two divisors, right? Because the 0 of this will be 0, but 0 of this guy will become a pole, right? So this object is, the divisor of that is simply D1L minus D2L. And what we are seeing is that this must be a function, so this must have degree 0. That means, first of all, that these two must have the same degree. Okay? And secondly, is not just the fact that degree 0, but it is the divisor of a function. It's a divisor of a meromorphic function. Okay? So it's a divisor of a function. So therefore, there is not a one-to-one correspondence between the line bundle and the divisor, right? You can form an equivalence class. Okay, two divisors are identified. Okay, if they differ by a divisor of a meromorphic function. Okay, so that is the idea. So you say two divisors are identified if D2 minus D1 is a divisor of a function. Of a meromorphic function. So what you do is you actually denote this, you take the set of all divisors and quotient by this equivalence relation. Okay? And that you call a class, a divisor class. Okay? So this is a divisor class. So this is just obtained by taking the set of all divisors for a given line bundle and quotient by this equivalence relation. Okay? So this D is a set of all possible divisors quotiented by this equivalence relation. That's the idea. Of course, and also we learn that given a line bundle, degree is always going to be fixed, right? Degree of any divisor of any section will be fixed. A degree, of course, is an integer, right? I mean, because that's a number counting the. Okay. So there is a classification of all the line bundles by giving the degree, but that is not the whole story. Okay, there's a bit more than that, and then we'll come to that in a moment. Okay. Okay, that's now that's an important theorem, Abel's theorem. Abel theorem. This again, I'm not going to prove that. Abel theorem basically says that every equivalence class, every class corresponds in one-to-one to a line bundle. Okay, so there is a correspondence between line bundles and the equivalence classes of the divisor. Okay, that's the main result of Abel's theorem. Okay, so this is fine. Now, to proceed further and to understand how much more freedom one has apart from a degree. Degree is just one very gross quantity, right? Is there more than that? And that, oh, this picture maybe I shouldn't erase. 1, 2, 3, 4, 5. Okay. Yeah. Of a given line bundle, yeah. Okay, there is, okay, maybe how to introduce this. I think better to introduce a theta function first. Then it comes, this next definition will come naturally. Okay, I mean, you all have seen, I think, the one loop. At genus 1, the theta function, so g equal to 1. Theta function plays a very important role in all the partition functions, right? So what is theta function? Theta function depends on z and, of course, the tau. Tau is the complex structure parameter for the torus. One loop, g equal to 1 now. I'll generalize it to higher g. But first, let's look at the g equal to 1. Well, this is nothing else but e to the power of I pi n tau n. Let me write it like that. Tau n square, basically. Tau is just one complex number. Right, I should have said something. Okay, maybe I can say that later. Plus 2 pi I times n z. Okay. Summed over all n belonging to integers. This is a theta function.
Sorry, is multiplied by n, we have n? Or tau n?
Sorry, not hat. This was the, this one, n tau n, yeah. Tau n square. Tau n square, yeah. Because I'm going to generalize it, no? I've written like, yeah, here of course tau n square. Yeah, because there is only one tau. I should have mentioned this since, now, I mean, this was g equal to 1. G equal to 1, you had only one abelian differential, omega. And you had this, you normalize it, integral around a cycle is equal to 1. That you can always do. Whatever it is, you can divide by that number. You can always do that. And then the only quantity which is left over is around the B cycle, and that is some complex number tau, right? But there's only one. Now what happens for higher genus? We have several of them, AI, omega j, this integral, we can always normalize them to delta ij, right? This I can always do. If it's not 0, you can just redefine your omegas to normalize it. But then once I have done that normalization, then I have no more freedom left, right? Then whatever I compute, so let's say bi omega j, this will be some complex numbers, but labeled by 2 index, I and j, right? So this is each I and j go from 1 to g. So this gives you a g by g matrix, right? So this is these are the components, row and column vector. So this is, you can think of it as a g by g matrix. This is what is called a period matrix. Okay. Period matrix, yeah. Now, there are certain things you can show. This is not, that this is in fact symmetric. This period matrix is symmetric. Tau ij equal to tau ji. And the way to see this is the following. Let me see. Yeah, you can, in that picture is better. So see, if you take this integral of omega wedge omega I wedge omega j, okay, integral over the full Riemann surface. This, of course, is 0, right? Because both are dz. The wedge product is dz square will be 0, right? It's antisymmetric. So this is 0. But on the other hand, you can now do this integral around here and use the fact, write it like the following. Since on this in this polygon, you can always write, say, one of them, omega j, as d of some fj, right? This is now is polygon, it's not a, right? Of course, this does not mean that the value of the fj here will be the same as the value of fj there, right? But since this is now an open region, open set, you can solve it, right? You can integrate it. Or another way to say is that you can choose some base point p naught is here, or some point here, and then define this f by integrating omega j from there to there. Take any curve and integrate it. Okay? So that will define fg. Because these are closed forms. You can define it that way. And then substitute that there, omega I dfj, and then integrate by parts. Okay? When the d acts on this guy, it is 0 because omega is a closed form, right? So what you'll get is the boundary term, okay? And then you do this, so you have the integral over this polygon, okay? Now, let's take now, for example, if I look at these two guys, A1 and A1 inverse. Now, normally you would say it vanishes, right? However, this f, so what we'll get is that, so integral over omega I fj, right? That's what we'll get. But this omega I over fj, normally you would say that the integral from here and the integral over there will vanish, but that is not the case because fj is not the same here and there. In order to, if I take a point here and if I look at the corresponding point there, I had to go around the B cycle, right? So fj evaluated here minus the fj evaluated there is the integral of omega j around the B cycle, right? Okay. But that is tau. Okay. So by doing this, it's a simple exercise. You can just work it out. And then from here, you will find that this is in fact equal to tau ij minus tau ji. Okay. So remember that, so let's say if I look at this some point here, say x, and another point here, x, which is the same point. Before opening it up is the same point. Okay? But in order to go from this x to that x, let's say x prime, I had to go around the B cycle, right? So fj at x prime minus fj at x is nothing else but the integral of omega j around the B cycle, around the corresponding B cycle. So here is B1, so B1 cycle. Okay. So using all of this you can easily prove that this is equal to this, so it's symmetric. Incidentally, the same thing you can do it now for the omega bar. Okay, so I mean, you can take another guy, so omega bar I, another integral, omega bar I, omega j, and this you can show will be related to the im tau ij, okay. Imaginary part of tau ij. And then from there, because this must be, I mean, if I take any, multiply this by any xj, summed over j, and here multiply by the complex conjugate of x bar I, then you see this must be must have some definite, it must be I times some positive quantity, right? So that's what gives us a condition that im tau is positive. Okay? Just like in the torus case, imaginary part of tau was positive, right? Same thing, you'll get relations. So this kind of, that's why this is very useful. This picture is very useful. Cutting it open, and then you can, do a lot of manipulations and get many interesting results. Anyway, so upshot here was that tau now is a G by G matrix. So, I mean, this doesn't make, I mean, how can I generalize it, right? So the natural, this I don't want to erase. No. So if I look at this term, well, this term I can easily generalize, e to the I pi and I, tau ij, nj, right? But now I have g set of integers, n's. This I goes from 1 to g. So I have now ni, I going from 1 up to g. These are all in integers. But then what do I do with this? Well, there are g of them, so I better have g of z's, right? So then I should have 2 pi I and I zi, summed over I. I mean, repeated indices are summed over. Okay. So I should have so this zi, this is an element of g-dimensional complex space, CG. Now, how can I mean, on the other hand, we want objects living on the Riemann surface, which is one complex dimensional, right? On the other hand, theta functions I can define only for where the z's are in CG. Okay? And that is done by something called, I think, there's an Abel map. Actually, I'm not sure. In some literature, I find this is called Jacobi map, but in some other literature, I find it's called Abel map. So I'm not sure. Maybe you know. I don't know. Anyway, so it's some map. Anyway, that maps sigma g to this CG. Okay, and it's done in a very simple way. Choose some base point. Some base point here. Doesn't have to be this here. Any base point. Choose some fixed base point. Okay. So choose some fixed base point. Base point. Let's say, call it P naught. I mean, as I said, this need not be that vertex. Could be any base point. And then define this map, a point Z belonging to sigma g, point P, let's say, point P belonging to sigma g is mapped to P naught to P of omega I. Okay. So you just take a path connecting P naught and P, integrate this omega I. Since I goes from 1 to G, this gives you a set of G complex numbers here, right? So therefore, this belongs to, when I take all the values of I, this belongs to CG. Okay. So this is the map. But it is not, I mean, this map is obviously is not unique, right? Because now, yeah, I mean, precisely. So if I take the point P naught here and point P here, I mean, one path you can choose is just that, for example. But you could, somebody else may choose a path which is like going around here and coming back here, no? Or going around the B cycle and coming back here. Okay. So given any path like that, I could add to this path any number of A cycles and B cycle. I mean, I could go several times in different A cycles and B cycles and come back to point P. What will be the ambiguity? Ambiguity will be that if I do that, it will, so let's take, so a general path would be choose a fixed path, so like that, plus it could be any number of A cycles, Ni, plus any number of B cycles, right? You could wind around. And then now I'm going to integrate over all of that. Then what I will get? I will get the original value, P naught to P omega I, plus Ni, I should, no, Nj omega Aj. Okay, so Ni plus Nj tau Ij. Okay, so it's not a unique point in the CG. However, the difference is of a very particular type. I mean, the different choices will give you points which are differing by integer plus, I mean, set of integers plus integers times the period matrix. Okay, so what you define is you quotient the CG by that freedom, and then it's a one-to-one. Okay. So what you're doing now is to take so that's called Jacobi variety. So you define, let's see, so the Jacobi variety is simply CG modded by Z to the G plus tau Z to the G, let's say. Mod out by that. I hope this notation is clear, right? These are n integers. Okay. Other guy is G integers, and this guy is a G integers multiplied by tau. So that's what that notation means. You identify. So that's the Jacobi variety. And inside the Jacobi variety, these points are mapped to a unique point. A point on the Riemann surface is mapped to a unique point there.
The Jacobi variety is the tau itself.
Yeah, correct. Yeah. So that's why G equal to 1 was so simple. I mean, here, Okay, so then I can define. So therefore, you see, I mean, to begin with, I can define this. So I can define a theta function, which will be in general for some z tau, but now this is in CG, right? And the tau is, of course, a G by G matrix. And that is exactly the same expression. It is I pi tau, and sorry, now I should write it as n tau n, or more precisely n transpose tau n, plus 2 pi I n transpose z. Right? You can do that. But this is still a function on CG. If you want to write it as a function on the Riemann surface, then take the z, so theta of whatever z of tau, or in general it can be many z's, zi's, z in the index, some a's, tau, and I can. So there are several z's here. These are all points on the Riemann surface. Maybe I shouldn't use z. I don't know. Let's call it point PA's. All of these points I can map it to. So sum over PA, let's say sum over PA. What it means is the sum over PA, this notation. This is an abbreviation. What I mean by this is nothing else but this Jacobi map. P naught to PA summed over A of omega I. Oh, by the way, this relation, I mean this ambiguity here, it doesn't create too much problem for the theta functions, right? Because, I mean, when I make a shift by Ni plus Mj tau ij, there is definite monodromy property, so this quasi-periodicity property of theta functions, right? For example, if I shift by integer, if I shift these z's by the integers, nothing happens, right? When I shift by this m times tau, what you do is that you can redefine this quantity, and the new sum will be over n plus m. So up to some overall phase factor, you will get the same theta function, right? So this is the quasi-periodicity of theta functions, which means this is basically is a good object on the Jacobi variety, up to some overall phases. So this is the way one defines. One defines a theta function. Now,
when you have sum of the point, you are thinking of a kind of sum of vectors, because the sum of points is actually a vector in the Jacobi.
yeah, it's in the sense of a divisor. Okay, so what I'm saying is it's a divisor. So take any divisor. So basically, I can write it as some divisor. Suddenly, the voice changed here. So take a divisor, then what you do is you map that divisor to the Jacobi variety via this Abel map. So what you do is if I have a divisor which has sum over p's minus sum over q's, that's a divisor, let's say, then this is mapped to p naught to pi omega p a omega I minus p naught to qb, let's say, omega I.
And this is zi. This is zi.
This is zi, yeah. This is zi, yeah. This is a summed over a sum over b. Okay. This is what we'll call zi. So as we said, of course, there is this ambiguity. But that ambiguity, if I plug it in here, it's just some overall phases.
Sorry, just to be clear, it depends on Z.
Yeah, that depends on the, Theta function usually, under the B cycle, when you go around the B cycle, which corresponds to that, then there will be a Z dependence also. I mean, I will write down explicit formula for that in a moment. I mean, the monodromy properties. Okay, so this is the theta function. So for every divisor, notice that if the divisor has degree 0, then something nice happens, because the number of these guys is equal to the number of that, so the base point disappears. I mean, you don't need to worry about the base point. But you can do it. Once you choose a base point, you can just choose any divisor, and you can get that. Okay. Now, let's see. Now, there are, I mean, if you think about it, you see, this is I mean, the way I have defined here, okay, this is when we want to go to the Riemann surface. At the moment, it's just a function on CG, right? Oh, sorry, what is the time? How much I have? I have still half an hour? Okay. So this is still a function of on CG, G-dimensional CG. But theta itself is one complex number, right? So this theta function is basically mapping CG to a complex number, right? So obviously there is going to be a lot of zeros, right? I mean, in other words, if I fix this value here, there should be G minus 1 dimensional subspaces in the Jacobi variety, which will give the same value. I mean, so, you kind of roughly assume. Huh? Yeah, it's not meromorphic because this is, you see, there's just a Fourier expansion, right, in the Zs. So there will be no singularity, no singularities. Yeah. But this is quasi-periodic. No? It's yeah, but I mean, it's the theta function itself is not a good function defined on the Jacobi variety because there is a multipliers. No, these are quasi-periodic. So when I, where is it? This guy, this equivalent, I mean, the CG modded by that. But under this, nothing changes. Theta function is invariant. But under that, theta function goes to itself times something. No? So it's not. Shift.
The completion of the square.
That's right. Yeah. Okay. So now, so one important thing one can ask is, where are the zeros of this theta function? the zeros of the theta function. And this, yeah. So let me be more precise here. Okay, I should be much more quick now. Yeah, so let's define a function f. Okay, the problem is that I can't see. Doesn't matter. Let me see now. F. Yeah, so f is something like this. Let's define it like this here. Theta of say z or p or something. So I take this from the base point p naught to some p. Let me just call it z, omega I, plus ei. Ei is any element in CG. Okay? Any point in the CG, tau. So let's call this. So this is a function of z. Right? I think of this as a function of z. Okay? Of course, it's quasi-periodic and so on. I mean, but nevertheless, it's some function. So what we want to ask is, where are there values for z for which this becomes 0? Yeah? How many zeros are there? There are no poles because, as we said, this is this function is finite. I mean, there's no singularity, right? But it can have zeros, right? So are there zeros? And that you can again obtain by maybe I should write this, the monodromy of the theta function. Let me write this monodromy equation. Theta of, I will just, to shorthand notation, I will just call it z. Huh? Okay, I will just call z. But this is a point in the Riemann surface. Okay, but by that I mean the Jacobi map or Abel map of z to CG. So this is a shorthand notation. Or should I keep it? I don't know. So, okay, well, that's that. Yeah, I wanted to write the monodromy. So let's write it as this plus tau n plus m. Okay. So we want to look at this monodromy. This is the shift by this object. This is again n integer, g integers, g integers. It's all g dimensional. Okay. Arguments are all g dimensional. Okay. This tau is equal to, which is a very simple thing, just by like we have done many times in the genus 1 case, you can show that this is nothing else but I pi n, this n, tau n, minus 2 pi I n z times theta of z tau. This is done by just making it a whole. If I shift by m, nothing happens, right? I mean, if I shift m, this is just e to the 2 pi I times an integer, it's a phase. Nothing happens. But when I shift by tau n, this n, okay. I don't know, let's call it k and l, okay. K, L. K, okay. So then you will get a k, tau k, but then you can make it into a whole square by shifting n to n plus k. Right? But then you have to subtract that k extra pieces. And when you subtract the extra pieces, you get that. Okay, this is a very trivial thing. That is the monodromy. But now to find the zeros of this guy, again, do the same thing. Take d log f. D log f, I mean df over f. And integrate over around the polygon. Right? Is the Greens theorem. This is the Greens theorem. I mean, using Greens theorem, basically. So you integrate around it, but now the A1 cycle and A1 inverse cycle will not cancel. Okay? Because a point x here and a point x prime, which are related to the same point on the Riemann surface, in order to get there, I needed to go around a B cycle, right? B1 cycle. But when I go along the B1 cycle, this is precisely the k shift, right? So you see, you get, so the two values are not the same. Okay, so if I look at f at x prime and compare it with the f of x, f evaluated at this point and f evaluated at x prime, then by using this relation, you see, you find that f of x prime is e to the power of minus I pi k, k is 1, so tau 1, 1, because I'm talking about the A1. So this is going around B1 cycle. So tau 1, 1 minus 2 pi I Z1. Okay, Z1 meaning this is the same as P naught to P Z, omega Z, omega 1 Z. Omega 1, I mean, okay? P naught to Z, sorry, I'm getting confused here. Okay. So you pick up that piece times f of x. This just comes from this monodromy of the theta function. Okay. But when I take the log, I mean, this is nothing else but the log. So log of f of x prime will be this thing plus log of fx. Okay. So the log of fx piece will cancel, but you still pick up that piece. And when I take the derivative, I have to take the d of log f. It will precisely pick up omega at z. Okay. So that's what you find. So you get omega 1 of evaluated at z, but then I have to do the integral of this x on the A cycle. So I'll pick up 1, right? Because omega 1 integrated around A1 cycle is 1. Okay. And this you can do for every cycle like this. On the other hand, if I compare the B1 cycle and B1 inverse cycle, there's no, it just exactly cancels. Because in order to go from a point here and a corresponding point there, I needed to go around the A1 cycle. But around A1 cycle, there is no monodromy, and monodromy is trivial, right? So the B1 cycle integrals will exactly cancel, B1 and B1 inverse. But A1 integrals will not cancel. There's a shift, and that shift simply gives a 1 for each I. Right? So you find that this integral around this boundary is nothing else but g. Again, 1 over 2 pi I. Okay. That is g. Okay. I mean, you can, just by using the monodromy, you can check it. That is g. So therefore, we see that there are g zeros. Since we know, so this will be, the g will be the sum of the zeros minus sum of poles. But there are no poles because this is finite, there's no singularity. So we conclude that the zeros of theta function, there are g zeros. So as a function of z, there are g positions where this vanishes. This is a famous Riemann banishing theorem. This is very important, actually. Theorem. So it will have some g zeros. Let's call it p1 up to pg. Okay, g zeros. Then there's another important statement here. So what are these zeros? I mean, what is the relation? Well, if I take, let's see. Yeah, and those zeros you can, so you can prove the following statement also, that, sorry. Uh-huh.
Is it possible to write as a ratio of theta? Because
I don't remember now.
Because the p has two zeros and a function. Let's say a function has the same number of poles and
yeah. Okay.
You could wonder whether you can write
function.
as ratios
Or theta functions on a genus 1, right? On genus 1. Here also you can write actually any meromorphic function in terms of something called prime form. But this is what we are heading towards, prime form. You see, the point is that on the torus it was very easy. Suppose I'm looking at a correlation function. Let's say some correlation function of 2 fermions, for example, right? psi with psi bar. Then we know that by OPE, they should have 1 over z minus w, pole, right? And theta 1 of theta 1, odd spin structure, theta 1 of z minus w precisely had that property that vanishing only at z equal to w. So you can then construct the correlator functions on. And of course, you can use to construct any meromorphic functions with prescribed number, value positions of 0 and poles in terms of products of theta and ratios of theta. Now here, on the other hand, it is not the case. You see, I mean, already we see there are G zeros here, right? So yeah, exactly. But that's where we are heading towards. We'll construct something called a prime form, which will have exactly that property. And then you can use prime forms to construct any objects. Yeah, that is a crucial ingredient for a correlation function, propagators and so on. I mean, these are called theta divisors. I mean, it's related to theta divisors. But okay, at the moment we are just saying I consider this function z, and it has some zeros. I mean, I just call them p1 to pg. Yeah, but you see, this theta function is not even. I mean, this is even quasi-periodic. It's not even. This is for arbitrary d, no?
Yeah, but if you want to
function, but it doesn't. Yeah, but you don't have to. You can keep p naught. It doesn't matter. Yeah, you can keep p naught. Yeah, but I mean, so what it is that that's a very important point here. That there exists something called Riemann. Riemann has done so much work, you know. Yeah, amazing. Yeah, Riemann theta constant, which is usually in the literature denoted by delta, not to be confused with the conformal dimension, delta. So this is Riemann theta constant, and the statement is that this E, you can express this E. This EI, remember this point EI. This is just an arbitrary point in the CG. But you can express this CG, this delta, this EI, E, let me just call it E, as delta minus some EI, and some P naught to pi omega pj omega I summed over j going from 1 to g, because there are g zeros there, right? So you can write this EI in this way. I mean, this is a matter of definition of delta I, right? I mean, you can always write it like that. But this delta I, and one can write down a formula for the delta. We will never need it. Okay, there's a delta which is just depends on the this just depends on the base point, choice of the base point p naught, nothing else. So it's something you choose your surface and a particular marking. This is what is called a marking. Okay, and the base point p naught. Then delta depends on the p naught. Delta itself is a divisor class of g minus 1. Degree g minus 1 divisor class. Okay. That is there. And so then you can write it like this. But then, if I substitute that back there, then you see that f of z becomes. I mean, one can write down an explicit formula, but we will never need it. This delta you can write on an explicit formula, but we'll never need it. So this f of z, you can write it as theta. Just substitute that back here. You'll get here p naught to p naught to z, plus delta minus integral this guy. P naught to Pj omega j. So this is all omega j, delta j. Okay. So that's what we get. The point here is that these are precisely the positions where that function f of z has vanished. But now notice, if I take the z and put that z to one of the pj's, then it is 0, identically, right? Because that's exactly the 0 of this f of z. So we come to this conclusion, and this is very, very important conclusion here.
PJs, you are writing that expression zeros
Of the original function.
Okay.
Of f z. Yeah, sure. I mean, that's, these pj's are the zeros, are zeros of f of z. Okay, so now we put, so now I set z equal to one of the p's. So put z, take it to say one of them, say pg. Let's take that, pg. Huh? Then what do we get here? We get theta of, so z goes to pg, that term cancels here, and you are left with simply theta of delta minus in sum over j going from 1 to g minus 1 now, pj p naught. This is 0. See. That's, and now you see there is no reference to the original function f. So this is completely general. For any pj, it's okay. It vanishes. Okay. So if I take g points, any arbitrary g minus 1 points on the Riemann surface, and compute this theta of delta. Delta is this particular constant, which I didn't write the expressions for. But if you write that, use that expression, is something fixed. This depends, as I said, only on P naught. Then this is vanishes, identically vanishes. Okay. Function of the? For arbitrary PG, I mean, take. Yeah, because now you see this has no reference to the original function f. Okay, this could be any PJs, it doesn't matter. Okay. Yeah, I mean the point is delta will be independent of PJs. You see, delta is independent of PJs. So delta is only a function of P naught. That's. So this is vanishing, this identical result. So there are sigma g to the g minus 1. These are because there are g minus 1 points. Okay. This identically goes to 0. So theta maps to this to 0. Theta with this delta, shift to delta, maps to 0. This is all part of the same Riemann. In some textbooks, first they prove that, and then they prove this. You know, this, or in some others. So they're equivalent statements, actually. All right, now what I should do. Can't find it. As I said, delta is a divisor of G minus 1 divisor class. And one can actually, so let's see what is the degree of the canonical bundle. Canonical bundle is once again consider this differentials, one differentials, omegas, right? So in general, so one differentials. So line bundle of one differentials, which had holomorphic sections, right? There were G holomorphic sections. Those were the omega i's.
So essentially, the delta are kind of primitive integral of the sum, because if you move p naught to a q naught, they compensate for the shift of p0. EI are independent.
No, EI depends on the PJ, but delta does not depend on the PJ. I mean, EI is defined here.
Yes, or dependent on PJ.
Yeah.
But if you take P naught, the basis point, and
Yeah.
you move the basis point.
True, it compensates for that. Exactly.
Yes.
Exactly.
So, in a certain sense, it is the sum of
Yeah.
omega I between P0 and P first 0 is the difference.
Yeah, exactly. Because that's why I said also this is degree G minus 1. So you can think of this again as some divisor of degree G minus 1 integrated from P naught to that divisor, right? So then the P naught cancels actually in this combination. This particular combination P naught cancels. So this has a P naught dependence, but this combination has no P naught dependence, right? So what I wanted to say was that this line bundle has a special, usually they call it canonical bundle. Canonical bundle. And its degree, so, there is another way of computing the degree of a line bundle, that is by just looking at the connection, which defines a line bundle, and computing the curvature of the connection. The curvature for this one differential is simply whatever the Riemann, this is the curvature tensor of the worldsheet, or the sigma g, right? So this will just be the Euler characteristic of the sigma g itself, standard Euler characteristic of that. And that is from that calculation you can find that this canonical bundle has a degree 2g minus 2. Okay. This will be equal to minus the Euler characteristic chi. Chi is 2 minus 2g. Okay. This you can see by just simply using the standard formula, v minus the edges plus the f, the faces. Okay. You triangulate your Riemann surface and count the number of vertices, number of edges, number of faces, and when you compute that, you will find it's 2 minus 2g. Okay. You can take, the way to do it is take the sphere. Again, the construction was take 2g holes and then start connecting this. And then you can see every time I add such a tube, what am I going to get? You can triangulate this tube here, and you'll find that every time I add a tube, I will remove an extra minus 2. So this way you can get that. So easy to do it. Anyway, that's the answer. 2 minus 2g is the Euler characteristic. So the degree of the canonical bundle is 2g minus 2. Okay. And this is degree g minus 1. Delta is degree g minus 1. And 2 times delta is in fact equal to the canonical bundle. Okay. 2 times delta is a canonical bundle. So it's actually, it's quite interesting that that's actually the bundle is one of the spin structure. It's a bundle for the half differential, which is the fermion, in some spin structure. Okay. In some spin structure. So that is why this delta plays a very important role in all these correlation functions. Delta is one of them. So the conclusion from this, okay, I'm here being very quick, but the conclusion here is that delta is a bundle associated with the spinors, bundle associated with the half differential. Half differential means a fermion, right? A worldsheet fermion in a particular spin structure. Let's call that D naught. D naught is that spin structure. Okay. Then what about all the other spin structures, right? Well, all the other spin structures is just simply shifting by half the, like what happened in the torus, right? You shift by half, both along the A cycle and B cycle. Just flip the boundary conditions. Okay. So a general spin structure will be, I can write it as D0 plus 1/2 plus alpha 1 plus tau alpha 2. Okay. Where these are all alpha 1, alpha 2, etc. There are, this is in the alpha 1 and alpha 2 are in Z to the G, 1/2 Z to the G, mod Z to the G. Okay. These are half integers.
The reason why you are doing that is that if you take the divisor of D0 as degree, you wrote before it as degree D minus 1, and if you square it, you get the degree 2 minus 2, which is the degree of
True.
K.
But it's more than that. It's exactly the same, because remember the degree itself doesn't define the full line bundle, right? You need to specify degree and a point in the Jacobi variety. Okay. But here it happens that the point in the Jacobi variety is such that the square of delta, square of this line bundle, or which means 2 delta, is actually exactly the canonical one. So it's a bit more than that statement. Yeah. Okay. Yeah, true. So 2d0 is k. 2d0 is k. Okay. But so is 2d alpha. Right? Because if I take multiply by 2, so this guy is 2 times d0 is k, and this guy, you see, these are all half integers. There are g of them. This is a g-dimensional vector. G-dimensional vector. Because a tau is a g by g matrix, so we are talking about a g-dimensional vector. So these are all I'm writing in the sense of, again, able map. So divisor has been mapped to a CG, point of CG. So this is again a point of CG, again a point of CG. But these alpha 1 and alpha 2 are just half integers. Okay? So when I take multiply by 2, I'm going to get 2 alpha 1 and 2 alpha 2 here, but those are integers. But that we are modding out when you define the Jacobi variety anyway, right? I mean, you remember Jacobi variety was defined as a CG modded by integer plus tau times integer, right? So those are the same points. So therefore, 2d alpha is also k, the same class. Okay. So these are all the spin structures. Huh? Sorry? Yeah. This is all of them. All the spin structures are here. D0 picks up the E1 spin structure. Yeah. Sorry? Yeah, correct. There is no positive divisor. Yeah, there will be always some poles. Yeah, correct. Yeah. So yeah, D0 is so this is all the spin structures, and you can count how many are there. It's clear, right? These are all half integers. You'll find 2 to the power of 2g integers. Because this is g-dimensional vector, that's a g-dimensional vector. Each entry you can choose either 0 or half, right? So you'll find 2 to the power of 2g spin structures. Now you can write down, just like in the genus 1 case, we could write down the theta functions, right? Remember we had theta 1, theta 2, theta 3, theta 4, right? And we can do the same thing here. So all we need to do is to define, so theta of, let's say, I think alpha 1 and alpha 2, let's say. So this is, each of them is a g. There are g informations here, zt, z tau, will be simply theta of, e to the power of I pi n plus alpha 1 tau n plus alpha 1, okay, transpose, plus 2 pi I n plus alpha 1 z plus beta alpha 2. Right? This is exactly the generalization. Only thing is these are all g dimensional objects. Yeah. So sum over n, yeah, sum over n, exactly. Sum over all the ni's. Okay. Okay. So this is the thing. And now from here, we can easily derive that for some choices of alphas, this function will be an odd function of z, or in some other, in other cases, it will be even functions of z. So you can separate them into even and odd. So one can prove from here, one can prove from just from this definition that alpha 1, alpha 2 of minus z tau equal to minus 1 to the power of 4 alpha 1 dot alpha 2, okay, times theta of alpha 1, alpha 2 of z tau. Dot. Huh? This is a dot product. So in other words, in the matrix notation, it will be alpha 1 transpose alpha 2. Yeah. So then this, this will tell you, so the ones where this is odd, of course these are integers because alpha 1, alpha 2 are half integers, but is multiplying by 4. So this is always an integer, but the possibilities it could be even or odd, right? When this is odd number, that will be odd function of z, and when it is even, it will be even function of z. Okay. So this will split into, I think, half times 2 to the g minus 1. That will be the number of even guys, and half 2 to the g minus, plus 1 and minus 1. That will be the odd guys. Okay. So this is that's the way it composes. Okay. Now we come to the. Can I just take another 10 minutes, maybe 5-10 minutes? 5 minutes, because I want to arrive at the prime form, which is the most crucial thing. I mean, going back to the construction of all the propagators is related to the prime form. Okay, the prime form is constructed something like this. So let's start from this object, and let's look at an odd spin structure. Odd spin structure. Choose. Huh? Sorry.
Prime form is a name? Or?
Yeah, it's a name. Yeah, prime form. Prime form. Prime form. I will just define that. Just in a few minutes, I'll define prime form. Okay. So let's start with the odd spin structure. Take any odd spin structure. It doesn't matter which one. So of course that means if I take if I have the odd spin structure, let me just call it alpha. So alpha 1 and alpha 2, I'm just calling it as alpha put together. And the important point is I'm taking it to be odd. Okay. Then we know that this is 0, right? Because the odd character. Okay. So now let's define a function. Let's define a function which is, okay, depends on this alpha, which of course is odd, but there are several odd spin structures here, right? I could have chosen any one of them. So it will depend on that, of z and w, 2 points on the Riemann surface. And this is simply defined as theta alpha of z minus w tau. Yeah. By z minus w, of course, I mean Abel map, right? So it's really the integral zw of the omega i's. Okay. Now, right. Actually, maybe I should have mentioned something else here already. Yeah, actually, I could mention something here that you see, I mean, There are two ways of writing it. One is to write like this, theta function. Other thing is you can take this object and put it inside the z. Okay, you can do that also, right? Just put it inside the z. Just open it up. Open up this guy. So there will be n square term. There will be alpha square term. Okay, that's an overall thing outside. And then there will be alpha times n. Okay, that alpha tau n, I can put it inside the z here by shifting z by tau times n, right? Tau times alpha. You shift by tau times alpha. So you can equally well think of this. You can put it inside here, and so this will be. I can also write it as theta of no characteristic here is simply z plus alpha 1 tau plus alpha 2 time of tau. And then there is some phase here. There is some phase, the usual phase that you need, like this alpha square term, etc. So there will be some phase here. So you can write it like that. Okay. Yeah.
So that object is vanishing linearly in Z minus W.
Yeah, it is. Yeah, exactly. So think about that. As a function of Z, how many zeros there are? And you find, so there will be, by Riemann, zeros, so there should be G zeros, right? One of the zero is clearly a W, right? So let's say, so the zeros are, let's suppose, the zeros as a function of Z are at Z equal to W and some other points, some G minus 1 other points. Let's call them SI. Because total number of zeros is G that we have seen. As a function of W, where are the zeros? Well, by the fact that it is odd, I can rewrite it as the exchange the Z and W overall minus sign. Okay, that doesn't matter. So W and Z are exactly in the same footing. Okay, so the W will have 0 at Z and again the same SIs. Okay. So now let us look at the point. So let's look at let's suppose this is S, some SI. Okay, and look at Z and W also in some small neighborhood of SI. So the Z is somewhere here, let's say, and W is somewhere here. Okay, they are all in some small neighborhood of SI. How will this function look like? Okay, this function will look like something like Z minus W, Z minus SI, and W minus SI. Right?
The local you are fixing W, and you are looking to the zero in the function of Z.
Yeah. So this is just as a function of Z.
But this is just locally because you cannot actually write this expression.
Oh no, this is in a small neighborhood. Small neighborhood.
You are not assured that there are other zeros.
No. This is odd. I have some G zeros altogether.
Yes, but one is obviously W.
Sure. Yeah.
But you are not sure how many others there are.
No, I know there are G minus 1 zeros.
Yes, but if you're in a small neighborhood, are you sure that are all of them in a small neighborhood?
No. This is one of them. S1. Take S1.
Okay, but
Right.
are you sure that there is one in a small neighborhood?
You can take as small as you wish, so long as the points are distinct. You can make it smaller and smaller, the neighborhood, right? So that in that neighborhood, there is just one zero. Or only one of the S's. So long as its S's are distinct S's, okay, then this is true, right? On the Riemann surface, let's say this S1 is one point here, S2 is another point here, whatever. Maybe these two are very close, but I can take even a smaller neighborhood around. No? So long as they're distinct. Okay, if they are the same, which means the second order is 0. But I'm considering a first order 0.
So you are choosing W closer to the number of zeros or...
Yeah, both Z and W close to that one point.
The view is not taken in whichever place.
No, everything same point. But there's a reason for that. I'm just coming to that. Yeah.
So the view is you have chosen closer to SE.
Both Z and W. Okay. So if I choose both Z and W in a small neighborhood of S1, then it will behave like this, plus higher order terms. But the leading term will be something like this. Okay. So Z minus W, Z minus SI, whatever the ith one, and W minus SI, times some constant. That will be the leading term. Okay. Now, if I take the derivative of F alpha with respect to, say, W, okay, and then set W equal to Z. Okay. Suppose you do that. Then what will happen? Okay, this derivative can hit here, can hit there, right? But if it hits here, that's no good, because then after that I have to put W equal to Z. So then it will vanish, right? So the leading term will be when this derivative hits there. Okay. When it hits there, this disappears. And then I put W equal to Z. So you see, this guy behaves like Z minus SI square. Okay. So that means that this function, now it's a function of only Z because W has gone away. This function of Z has double zeros at each, and this you can do for every SI, right? So we are concluding that this object has double zeros at each of the SI. Okay. So, and there are G minus 1 points. So the total degree is 2 times 2G minus 2, which is exactly the degree of the canonical bundle. Okay. In fact, we can even do better. We can explicitly see that this is the, let's explicitly take the derivative. Sorry, just 2 minutes more. Because I want to arrive at the prime form. And then, okay. You can explicitly do this by just take the derivative of this defining equation, right? Derivative with respect to W. So you will get some omega. I mean, W is this here, the endpoint, right? I mean, one of the limit points of the integral. When I integrate the W derivative with respect to W, will give me this integrand, right? Evaluated at W. So it will be omega I evaluated at W times d by dzi. I mean, by d, I. This is CG, right? So sorry, I shouldn't confuse with the Z. Okay, I don't know, what shall I call? D, let's say, I don't know, some symbol. Zeta, let's say Zeta I. Some Zeta I of theta of, let's say, W to Z, omega I, plus Zeta I, let's say, tau. I can write like this, and set Zeta I equal to 0. That's when I first took the derivative. But then after taking the derivative, I need to put W equal to Z. Okay. When I put W equal to Z, what I find here is that this becomes, this after W equal to Z, you find this will be omega I at Z. And then di of theta, W equal to Z, this disappears. And then is simply theta I, theta by d psi I, tau, and then set psi I equal to 0. Okay. This object does not depend on Z at all. Okay, these are some numbers. Only Z dependence is here, but these are one differentials. Okay, so very explicitly we see that this operation of doing that, taking the derivative and setting W equal to 0, W equal to Z, this gives you a one differential. So it's not surprising that the divisor class is also the same divisor class, right? Its degree is 2G minus 2, as we saw. So what we are saying is that this object, I don't know, give it a name, let's call it H alpha. H alpha is a function of Z. So H alpha, so this is H alpha. And what that argument is showing is that H alpha Z has double zeros at Si, where I going from 1 up to G minus 1. So the divisor is simply, so this divisor is simply 2 times sum over Si. I going from 1 to G minus 1. So degree is 2 times G minus 2, 2G minus 2, which is the canonical bundle, which is the divisor of the canonical bundle. And indeed, we see explicitly, no, let me not call it HI. Okay. No, let's not call it something. Let's not give it a name. Okay, no, okay, fine. Okay, let's call it H alpha Z. So H alpha Z is a one differential. But it's a very special one differential. It has double zeros, you see. When we say that any one differential has a 2G minus 2 degree, right? It will have 2G minus 2 zeros, but need not be double zeros. Okay? This construction, this is an explicit construction, which is a particular linear combination of these one differentials, right? Which is such that the zeros are all double zeros. What does that mean? That means I can take a square root. You see, square root is not going to produce any branch cuts. Okay? If there was a first order 0 somewhere, odd order of 0, and I take the square root, I'll get branch cut, right? But since it's even order, you will have no branch cut. So therefore, I can define a square root, and that is precisely the, so if I take the square root of that, square root of H alpha is well defined. Let's call this, I don't know, give some name, S alpha Z, let's say. S alpha Z, let's say. Okay. This will have G minus 1 zeros, that's all, so G minus 1 zeros at Si. At each point now it will be first order 0, because I have taken the square root. Okay. So the degree of this class is, the degree of this thing is precisely G minus 1, which is the degree of a spin bundle. And not only that, we see that square of that, in fact, is a canonical bundle. Okay. So that is a zero mode. That's a fermion zero mode in that odd spin structure. Okay. So we have an explicit construction of the fermion zero mode. Explicit as far as it can go. Okay. Now using this, now we can construct this prime form. Okay. And the prime form is, yeah. So let's take, I erased that. F alpha ZW is there. So look at this quantity now. F alpha ZW. Divided by S alpha Z, S alpha W. Okay. This is a function of Z and W. This is what's called the prime form E. Now let's look at the properties of this. What are the zeros? As we said, this F alpha has these zeros. Z as a function of Z, it is W and Zi. But then this guy has exactly first order zeros at Si. That means they cancel. So near Si, this will go like Z minus Si. This is going inverse of the propagator. Exactly. Yeah. So exactly. So this will go like Z minus Si, but this will also go like Z minus Si. So it cancels. Okay. So the only zero will survive. What will survive is Z equal to W. Okay. No other zero. And same thing here. As a function of W, all the W minus near the Si, they cancel also, right? So this object has exactly one zero. That is when Z equal to W, nothing else. Now, so it has a zero only at Z equal to W. That's one thing. Second thing is that this is, this object is a theta function, right? This guys are, as we said, these are half differentials. Okay, they're in the denominator. So this will transform as a function of Z. It will transform as a minus half differential, and similarly as a function of W, it will transform as a minus half differential. Right? I mean, this transforms as a half differential, but this is the denominator. So transition functions will be inverted, right? So that's why it's a minus half differential. So as a function of z and w, the transformation properties under coordinate transformations would be like minus half differential, minus half differential. And it has this property. And finally, it is quasi-periodic. It is not, because theta function itself is quasi-periodic, right? And one can write down the, okay, maybe I can do it tomorrow, next time. But I mean, just starting from this, we know the monodromy properties of theta functions. From there, you can deduce what is the monodromy property of E. In the A cycle, going around the A cycle, nothing changes. But going around the B cycle, there is a multiplier. So that is what it is. But so this itself is not going to be the Greens function, because it is not, or inverse of that is not going to be the Greens function, because it's still not, it's quasi-periodic, right? But this will be the important ingredient, actually the crucial ingredient in constructing the correlation function. Okay. So I think, sorry,